So Bill McGinty, who is the captain of the oil tanker HMS Slick, is so excited upon receiving his ultra-rare Noibat Pokemon card in his Burger King Poke Meal that he accidentally fires a flare gun through the hull of the ship, spilling oil, which spreads in a circular fashion, wreaking havoc on the Alaskan environment and ecosystem. And the question is, if the oil spreads in a circle whose radius is increasing at 6 square miles per hour, what is happening to the radius when the area is 9 square miles? In the question that was just asked about, that Christian asked about, the radius was increasing at a constant rate because that's the way the world works. That water wave will travel through the water at a constant rate. There is a reason why the rate of change of the area is constant here. And it's probably because the size of the opening in the hull is allowing a certain volume of water out every hour, and not water, oil, is allowing a certain amount of oil out every hour, and that means that the area has to be spreading at a certain amount every hour. We are assuming something here, and it's probably not entirely accurate, that the thickness of the slick is always the same. Which is, once it reaches a certain spreading out, that's going to be true. You know, you're not going to pile the oil onto the slick and the slick starts getting taller as opposed to wider. Okay. So how fast is the radius of the spill increasing? Well, we know dA dt, it is positive 6. We want to find dr dt, but the key here is when the area is 9. And there's just, the only thing that's different about this question, everybody, is there's an added kink or wrinkle in the work that you have to do. Because normally the question would be, what is the rate at which the radius is changing when the radius is 12 miles or something? Here you're told about the area. So we're back to the A equals pi r squared thing, which means dA dt equals 2 pi r dr dt. Getting kind of bored writing that all the time, but things will get exciting enough for your interest in a few minutes and later in the week. So now we can go ahead and put the numbers in. I'm going to put 6 for dA dt, 2 pi, and then I need to put in the radius so that I can find dr dt. The only issue is I don't know the radius. This is not a difficult problem. It's just one added layer to your solution, that you have to use your wits and everything at your disposal to determine the radius when the area is 9. Well, that's not difficult. We're going to put 9 in for the area and solve for r. And if A is equal to pi r squared, then 9 is equal to pi r squared. So r is equal to the principal square root of 9 over pi. There's no need or room for plus or minus here because r is a radius. Right? So I divide both sides by pi and take the square root. And what I'm getting for r then is 3 over root pi. The square root of 9 is 3, and then root pi, of course, is an irrational number. Another part of this question, and it's why I've made it this way, is I want you to get used to working with exact values. I think next year in post-secondary, many of you will go on and take calculus. And some of your TAs, the people who mark your assignments and things and exams, get very picky about exact values. It's not that you would, for goodness sake, you would never calculate what r is in decimal form and start loading decimals up here. Right? You want exact values to the end. Then if you want, you can do a decimal. So we're going to simplify this. I'm going to divide both sides by 6. 2 times 3 is 6. I have 6 on the other side. I'm left with 1. Then I'm going to divide both sides by pi and multiply both sides by root pi. And unless I'm mistaken, that happens to be dr dt. right? The 2 times the 3 on the right-hand side is 6, so I divide both sides by 6. I need to multiply both sides by root pi and divide both sides by pi to get dr dt by itself. So this is dr dt. Because root pi over pi is pi to the half over pi to the 1. And then I don't like subtracting exponents. That's not my gig. I don't care for it. But if I took the top exponent of a half minus the bottom exponent of 1, I get an exponent of negative a half, which means it's root pi on the bottom. I'm just as content to cancel, to say I have a pi to the half on the top and a pi to the whole on the bottom, so I get half a pi on the bottom. We could certainly work out what this is. One over root pi. Oh, good eye, Alex. Why is it going away? Okay, 1 over root pi, so you get 0.3, 0.2. Oh, I wasn't even close, was I? Oh, root pi. I was doing 1 over pi. Pardon me. How embarrassing. 0.564. So about 0.56 of a mile per hour. Oh, now it's moving. Oh. So dr dt is approximately half a mile per hour. Which seems pretty slow, right? I mean, walking half a mile per hour, that's pretty slow. But you're adding on a lot of oil to a circle that's really, really big, so you're not expecting to see it grow very rapidly. Any questions with example 5? Example 6, shortly after the incident happens, a Coast Guard patrol boat is 360 miles south of the HMS Slick. The captain flees, as you would do so in a situation like this, particularly if he's been drinking, maybe. He flees west at 100 miles per hour while the Coast Guard heads north at 120 miles per hour towards the scene. How quickly is the distance between the two ships changing 2 hours later? I hope you see that things have just switched gears here, right? This is considerably more complicated than a geometric shape changing its size. And this is a classic kind of problem where you have vehicles, whether they're ships or boats, moving perpendicular to each other. So what we want to do is draw a picture that we're going to use to develop a formula relating the distances involved at any point in time. Okay, so when it says 2 hours later, with a little bit of thought, I hope everybody would agree that 2 hours later, the captain's boat will have traveled 200 kilometers, or 200 miles rather. We can't use that 200 miles in our diagram. Okay. I hope you would agree that the Coast Guard boat will have traveled after 2 hours, 240 miles. But we can't use that in the diagram because that's a variable. That distance is a variable. So let's set it up by drawing, first of all, where the HMS Slick is to begin with. This is the initial position of the HMS Slick. And we do know that 360 miles south of that is the Coast Guard patrol boat. This is not a variable diagram because this is showing where the boats are at t equals 0. A variable diagram would show where the boats are at some arbitrary point in time later. And since the HMS Slick flees west. Sometime later, this boat, I'm going to make that a little bit longer. This boat will be there. And again, everybody, this is a variable diagram. I'm going in the wrong direction, aren't I? Okay. I often do that. If you've had me for physics, you know that I do that frequently. I use as an excuse the fact that you are facing the other direction than I am. Whether that's the reason or not, I don't know. So, travels west, and this distance here is a variable. So why don't we call it a variable? Okay. Because a short time later, the boat will be even further west, or a short time before, it won't be as far west. That's something that's changing. At the same time, the Coast Guard patrol boat is traveling north towards the scene. And I don't have to get out the drafting tools here, but I do want to recognize that since the patrol boat is traveling faster than the HMS Slick, it will travel further north than the Slick will travel west. Turns out it doesn't really matter. And since this distance is a variable, I need to call it something, and what better letter to use than Y, because that's a vertical motion. What we are asked to find is the rate at which the distance between the ships is changing. So we're asked to find what's happening to the length of that red line 2 hours later. And in reality, this might, practically speaking, be an engineering problem where you have parts of a crane. And one part of the crane is moving towards the top of the screen, one part of the crane is moving towards the left of the screen, and that red line is a cable, and you need to know a couple of things. How quickly is the length of that cable changing? And is the cable growing at that point in time or decreasing? And it's not entirely obvious. It could be growing at one point in time and then later on shrinking, or vice versa. So since that's the rate of change that we want to determine, that's the variable whose rate of change we want to determine, we need to introduce that variable. And I hope, well, let me write this down first. I hope that you can read the question, which I've cut off at the top of the screen, and tell me what dx dt is. Because they tell you what dx dt is. What is it? 100. It's 100. Right? And don't psych yourself out and go, oh, it's negative 100 because it's moving west. dx dt is positive 100 because the length of this line here that I'm going to highlight in blue, dx dt is positive 100 because that line's getting longer as time goes by. So dx dt is 100. dy dt, I'm sorry, is it 120? I just forget, 120. And those are miles per hour. And we want to find dz dt. And I will tell you right now that the biggest mistake that students make, and they make it whether or not I mention it or not. So at first I thought maybe I was planting the seed in people's heads. They don't make it as often if I mention it, but some students still do. You cannot write that. You can't, that doesn't work. That is not the relation between those three variables. The relation is a Pythagorean relation, but it's not x squared plus y squared equals z squared. If that were the case, then our y would be up here. It's not. Sometimes it is. Sometimes it might be as simple as that. So how are we going to use this diagram, I guess, to come up with a relationship between those three lengths, x, y, and z? And I've kind of intentionally left something off of the diagram that I could have put in. Do you know?
Would it be 360 minus y?
Yes. This part right here would be 360 minus y. And the part I have left off is this. That this distance is 360 miles. And I can put that 360 in the diagram right from the beginning, because no matter what those dots are doing, that distance is 360. And that means that this will be that 360 minus y. And now I have a Pythagorean triangle that I can base an equation off of. Hypotenuse squared equals short leg squared plus short leg squared. And I want to ask a question that I don't need to talk about this, but I think it's interesting. Can somebody tell me what's happening to 360 minus y? What's happening to that length, 360 minus y, when we start the clock? Fazile? It's getting smaller. It's decreasing. That component of the triangle is decreasing. What's happening to the component at the top, which is x? It's increasing. Keep that in mind for a second. And now let's differentiate. What is the derivative with respect to time of z squared? I wrap the 2 around the z, drop 1 from the exponent, multiply by the derivative of the base, which is z, with respect to time. I'm applying the chain rule here, or implicit differentiation. Plus 2x dx dt, not plus, equals 2x dx dt plus 2 times 360 minus y times negative dy dt. And that negative is important because even though y, everybody, has a positive rate of change, y is growing, when you apply the rules of differentiation, it turns out that this component has to be multiplied by negative 120. Why? To ensure that that vertical component is getting smaller. I mean, it isn't that the equation is a conscious thinking thing and this is why it's doing it. I'm pointing out that it all matches. Everything is consistent. The 2's cancel, and what I'm left with is z dz dt equals x dx dt. Well, how about this, you guys? I'm left with dz dt equals x dx dt plus 2 times 360 minus y times negative dy dt over z. Right? The 2's are gone, and I'm left with z dz dt equals that other stuff. And I forgot to, as he says, the 2's are gone, I forgot to get rid of that 2. So now there's a lot of legwork that needs to happen here, a lot of fishing around for numbers. Because we need to know x, we need to know y, we need to know z. We do know dx dt and dy dt. So if we go back up to the question, I don't think we need to justify this. After 2 hours, x will be 200 and y will be 240. It's a science 6 question. Train's traveling at 100 kilometers per hour. How far does it go in 2 hours? So we can put those numbers in. Let's see. X is 200. Dx dt is 100 plus 360 minus y, which is 240, times negative dy dt, which is negative 120. That look okay so far? Over z, well, we need to find z. Well, we already know x and y, and I'm not a real big fan here of creating a new problem by looking at the diagram and figuring out what z is. We have a formula for that, right? Why don't we just use the formula? We have z squared, I'll remember it, I hope. Z squared equals x squared plus 360 minus y squared. Okay. Z squared equals x squared plus 360 minus y squared Can you double check my math, my numerical math there? That 200 squared plus 360 minus 240 quantity squared is 54,400. Okay. Sometimes the level with which you're marked in calculus is kind of determined in part by tedious work. We need to simplify that radical. I see it ends in 2 zeros, so it must be divisible by 100. I see a bunch of 4s. I'm thinking it's divisible by 400. I'm looking for a perfect square. So that would be my kind of starting exploration here, is I would take 54,400 and divide by 400 and divide by 400. And what do I get? 136. Well, 136 is divisible by 4 again. It might even be divisible by 16, but no, 34. So if it's divisible by 400 and it's divisible by 4, it's divisible by 4 times 400. It's divisible by 1600. So if my logic is right, this is root 1600 root 34. And 34 is, it's not prime, but it doesn't go any further in terms of radicals. So can somebody just confirm, because I'm tired, I guess. Is 1600 times 34 54,400? Okay, so that means it's 400 root 34 miles. Whatever that is. 40 root 34. Thanks for that imperceptible, almost imperceptible look, Craig. I appreciate it. 40 root 34. So now I'm going to crunch the numbers on the top. You can crunch the numbers on the top as well. Does the top work up to 5,600? It does? Okay. It'd be really nice if 5,600 divided by 4, and it will. I want to say 140. So our answer as a simplified expression or value is dz dt equals 140 over root 34 miles per hour. And it's positive, which means the two ships at that point in time are getting further away from each other. Would it, we'll tie up the loose ends here in a second, but would it surprise you to know that if I said how fast is the rate, is the distance between the ships changing 3 seconds after it happens, would it surprise you to know that the distance would be shrinking at that point in time? that this is getting smaller at a rate of 120 kilometers per hour and this is growing at a rate of 100 kilometers per hour, it probably wouldn't be a big surprise to find out that they're actually getting closer to each other. But as time goes on, there's some point, it's hard to wrap your head around, but there's going to be some point where the captain starts making distance. There's nothing to be gained by rationalizing that. Nothing to be gained by rationalizing it. So let's figure out a decimal approximation. So approximately 24 miles per hour. I mean, almost precisely 24 miles per hour. And by the way, in calculus, we tend to use miles and feet, maybe just as frequently as meters and kilometers. There's lots of places in the world that still function daily with miles. I mean, I was in England over the holidays. Everything there is miles per hour and miles. You'd think they were in the metric system, but they're not. Any questions with that example? The big part of this, of course, is setting up that equation from that diagram. So does anybody have any questions? The bottom right corner of the screen here is just a little bit of extra work we had to do. A little side work. We're good? Okay, so the next set of questions. Page 145, 9, 12, and 13, and then there are additional problems. What do the additional problems look like? Let's see. Got an oil tanker, very similar to this, equilateral triangle. A couple of rectangles, but things get really dicey here now because we're talking about area and we're talking about perimeter. Not area and length and width, not perimeter and length and width, but area and perimeter. And there's a lot of, we're going to learn a lot by going over this question tomorrow. Okay, so get to work on those and let me know if I can help you.